Welcome to This Explainer. Today, we're tackling a massive bottleneck in the engineering world. We're talking about how to predict the exact strength of materials without wasting weeks on supercomputers. It's a real breakthrough in material science that's going to fundamentally change how fast we can design and test new components. Let's get right into it. So we're diving into a really fascinating paper from the International Journal of Mechanical Sciences. It offers a brilliant and honestly much-needed shortcut for a huge computational headache. We're looking at a brand new micromechanical model developed by researchers to predict the nonlinear elastoplastic behavior of short fiber reinforced composites. I know, nonlinear elastoplastic behavior sounds like a total mouthful, right? But stick with me, because the implications here are incredibly practical and literally game-changing for modern engineering. Let's start with a core question that keeps engineers up at night. How do we predict the unpredictable? Specifically, the behavior of materials as they bend, warp, and ultimately snap under pressure. When you're building a car or an aircraft, you absolutely cannot just guess how a material is going to hold up in a crash or under extreme stress. You need absolute certainty. There's no room for maybe. To understand why this is so crucial, we've got to look at short fiber reinforced composites, or SFRCs for short. These things are the absolute heroes of modern manufacturing. They give engineers the ultimate holy grail, super low weight combined with incredibly high stiffness. And because they can be efficiently pushed through injection molding processes, they can be formed into insanely complex shapes. Think of the intricate automotive parts we rely on every day. But of course, there's a catch. Here's the massive bottleneck we run into: accurately predicting their nonlinear elastoplastic behavior. Now, we aren't just talking about how a part bounces back from a light tap. We're talking about how it permanently deforms when pushed way past its elastic limits. Trying to simulate this currently takes an agonizing amount of computing power, especially because the way these short fibers are distributed and oriented inside the material can be incredibly complex. Traditionally, engineers have been stuck between a rock and a hard place. On one hand, you've got full field models. These simulate literally every microscopic detail. They're highly accurate, but they are painfully slow and computationally heavy. On the other hand, you have mean field models. These are super fast because they just assume average strains and stresses, but they completely miss the complex realism you actually need for advanced, safe engineering. So what's the solution? Well, the crux of this paper is a really clever new two-step orientation averaging framework proposed by the researchers. It's basically designed to give us the best of both worlds. You get the microscopic accuracy of a heavy, full-field model, but with the blazing speed of an averaging method. Let's break down exactly how they pull off this computational magic trick. To visualize the first step, imagine isolating what's called a unit cell. Think of this as just a single, solitary fiber, completely surrounded by a polymer matrix, sitting in its own little local coordinate system. By isolating just this one tiny piece, researchers can study the fundamental building block of the entire composite material without getting overwhelmed by the whole structure.
And this perfectly illustrates the heavy lifting. You're looking at a finite element mesh of that tiny unit cell for a polyamide and glass composite. They run a highly detailed, nonlinear finite element analysis on just this one microscopic cell to see exactly how the fiber interacts with the matrix when it gets deformed. But if you tried to do this across an entire car bumper, it would literally crash a supercomputer.
So here is where the genius shortcut comes in. Instead of rendering that complex 3D mesh thousands and thousands of times for an entire part, the researchers extract the data from that single-cell test. Then they teach a lightweight mathematical algorithm to act as its digital twin. They call this a calibrated surrogate constitutive model. And looking at the results, the shortcut works beautifully. Notice how the red circles, which represent those computationally expensive finite element results, perfectly align with the solid black line of our new lightweight surrogate model. It perfectly mimics the complex nonlinear behavior of the cell. We've managed to keep all the accuracy, but we've completely bypassed that massive computational drag. All right, let's move on to step 2 and see how this all builds together. Now that we have a fast, accurate model for just a single fiber, we need to perform what engineers call homogenization. Don't let the big word scare you. It simply means upscaling the mechanical response from that tiny microscopic cell level all the way up to the macroscopic composite level, the actual physical part you can hold in your hand. But here's the thing, an actual part isn't just one fiber, right? It's an aggregate of thousands of them, pointing in all sorts of different directions. To upscale this accurately, we have to solve a really nuanced Goldilocks problem. we need to figure out a mathematical interaction rule that correctly defines exactly how thousands of these individual fibers physically push and pull on their neighbors under stress. Translating the math into physics, the researchers looked at 3 different interaction assumptions to define the composite stiffness. The Voigt interaction assumes uniform strain, which gives us an upper bound. The Reuss interaction assumes uniform stress, providing a lower bound. But uniform stress or strain isn't exactly how the real world works. So the researchers proposed a third option to find the sweet spot, a self-consistent model. The self-consistent interaction is brilliant because it assumes each unit cell sits inside an equivalent homogeneous medium that represents the overall composite. Instead of assuming every single fiber is experiencing the exact same rigid force, it implicitly accounts for how neighboring fibers interact and share the load. It perfectly captures reality by finding the ideal physical middle ground. Of course, to prove this mathematical framework actually works outside of a whiteboard, the researchers had to test it against experimental data. Here, we're looking at a specific planar fiber alignment, a preferential distribution inside a polyamide and glass composite. They basically wanted to see if their algorithm could predict the behavior of a material where the fibers aren't just completely random, but actually flow in specific directions due to the injection molding process. They put their surrogate model to the ultimate test. They compared their orientation averaging method directly against a highly detailed, physically realistic 3D microstructural sample. They wanted to see for sure if the math mirrored reality. They mapped the aggregate response using their self-consistent interaction to evaluate its true predictive power against the complex 3D model. And the results? Honestly, they were incredible. As the researchers noted, the framework successfully captured the exact anisotropic behavior, meaning how the material reacts differently depending on which direction it's pulled. It also nailed the nonlinear stress strain observed in real-world physical loading tests. Whether they were testing a glass fiber polyamide or a flax fiber polypropylene composite, the self-consistent interaction provided exceptional agreement with the actual experimental measurements. But wait, the most dramatic payoff of this entire framework isn't just its accuracy. Think back to the major bottleneck we talked about at the beginning, computational weight. The researchers took a highly realistic, complex, 3-dimensional microstructure. First, they ran it through a direct computational homogenization. Then, they ran it through their brand new 2-step method. Here is the real mic drop moment. What traditionally required roughly 5 agonizing hours of simulation time on a supercomputer to process that realistic 3D volume, it was slashed down to just a few minutes using this new orientation averaging model. Let that sink in. 5 hours down to minutes while still producing highly comparable, accurate predictions. That is an absolute game changer for iterative engineering design. So let's look at the overall innovation payoff. This elegant breakthrough gives engineers a highly practical multi-scale simulation tool. It perfectly balances the intense accuracy of finite element analysis with the incredible efficiency of orientation averaging. And, critically, it accommodates arbitrary fiber distributions, large aspect ratios, and high volume fractions without completely choking your computer processor. So I'll leave you with this final thought. When engineers can test and validate the exact breaking points of complex composite materials in a matter of minutes instead of hours, how is this dramatic leap in simulation speed going to revolutionize the way we design lighter, safer, and more efficient vehicles in the future? The tools we use to predict the unpredictable just got infinitely faster. Thanks so much for joining me on this explainer, and remember to keep questioning the science behind the materials around you.